Carry on from last week, so this is AC analysis part 2. We're going to start with looking at the calculations around what happens with an RLC series circuit. So a resistor, inductor, capacitor, all three in series. So we've got an example circuit there. 10 ohms of resistance, 8 ohms of inductive reactance. So I'm not giving you it in henries, you don't need to calculate it. I'm giving you the impedance, the inductor, and 6 ohms of capacitive reactance. Alright? How can I express the total impedance ZT of that circuit in terms of all the other impedances? How do we calculate impedance in series? Add. So we got ZR plus ZL plus ZC. ZR is equal to, in terms of the circuit, yeah, that's equal to R. Yeah. The ZL is equal to XL. What have I got to add to that so that it is a complex form? So positive J. Yeah. For inductance. And then plus capacitive reactance. So XCJ, but it's negative J. Yeah? Yeah. Remember that from last week? So we can, the best way to bring that all together finally is to say that ZT is equal to R plus brackets XL minus XC, close the brackets, J ohms.
The second line that you read, is that ZT or ZR? Are they all ZT?
They're all ZTs. Total impedance. Yeah. Remember all these ones. XL and XC bit is the magnitude, and then the J gives you the angle. Positive 90 degrees, or positive pi over 2 radians, negative pi over 2 radians. Because Z, L and ZC are complex quantities. Yeah, they are vectors, direction as well as size. Okay, if we included the J for the R, it would be 0 anyway, so we leave it off. Alright, you're all happy with that so far? This bit here, together, what that means is XL is greater than XC, circuit is inductive, so overall, if XL is greater than XC, the circuit would be overall inductive in nature, despite containing some capacitance. If XL is less than XC, circuit is capacitive overall, despite having inductance.
Hang on.
Thank you.
If we draw the impedance phasors for this, we're going to have on the x-axis, what quantity would we have? What sits at 0 degrees?
That is.
Are we doing an impedance phasor?
Sorry, impedance. ZR.
Yep. 10 ohms. Yep. Then 90 degrees upwards is
The 8 ohms, that'd be XL.
right. 90 degrees downwards
XD.
Alright, now, what we have here is a third quantity that is the difference between these two. That is XL minus XC. That's equal to 2 ohms. Can you see that if the blue line was 8 and the red line was 6, that green one would go underneath. So that's the overall reactance. X is equal to the inductive reactance take away the capacitive reactance. So that controls whether the resultant phasor, which I'm going to do in black, we complete that parallelogram, and that in there is ZT. Yep, and that's got an angle in there, like so. So, as you're aware, these two quantities, XL and XC, are frequency dependent. So it's quite possible if we change the frequency of the AC supply for the conditions here to change, and that phasor to go underneath there and become an overall capacitive circuit. Yep. So depending on the relative size of these two phasors, there's also a condition we'll be looking at some point where these two are equal to each other and they cancel each other out completely. Yep. Alright with that? So, calculation-wise, we now have ZT being equal to R, which is 10, plus the 8 inductive reactance minus the 6 capacitive reactance, J ohms. Which is 10 plus 2J ohms. Alright? Now, if we're going to calculate the current, what would it be handy to do with that?
Transfer.
Yeah, so we can convert that to polar. We'll have our angles in degrees, please, because that's what I've got on here.
I need to change over. Yes. 10.19.
So 10.2 ohms.
11.31 degrees.
Yes, so 11.3. Yeah, so when you're doing these problems like this, it's worthwhile having both versions anyway, because then you can use the appropriate version later on in your calculations. Ultimately, if you're being asked to find the impedance, you want it in that form anyway, because that's the only form that gives you how many ohms it is and its angle. Yeah, you can't see that from 10 plus 2j. Right, you can make an estimate of what it is somewhere. It's going to be, because this is the larger quantity, it's going to be closer to 10 than it is 2. But other than that, you don't know. So polar form is always final answer form. Yep. Then what we can do is say I is equal to E, so the supply voltage, over the total impedance. That is 24. If the no angle is given, you assume 0, divided by 10.2, angle 11.3 degrees, equals. How do we do polar division of polar complex numbers?
Divide the first bit and then minus the second bit.
Yeah, so you do 24 over 10.2. I've got 2.35 amps. Angle 0 minus 11.3 is a minus 11.3 degrees. Worthwhile check. That's the current. Does it fit in with the word civil? We know the circuit's overall inductive because and this is why it's worthwhile drawing out the phasor diagram. We know it's inductive because the overall impedance is above this line. Yeah, the inductive reactance is bigger than the capacitive reactance. So we would expect in an inductor, using the word civil, for the current to be lacking the voltage in it is. Yeah, because the voltage is 0 degrees and the current is 11.3 in a negative direction. Alright? All okay with that? Yeah? Good. So that's just an intro into that. Right, what I want you to do now is have a go at this. So we're going to have a 5 ohm resistor. Ten ohms of inductance, 15 ohms of capacitance in series and connected to E equals 60 volts. VR, VL, VC, So calculate total impedance ZT, total current IT, calculate the three voltages around the circuit of VR, VL and VC, and use them to confirm that Kirchhoff's voltage law is being obeyed for that circuit. So, going through the results of this problem, part A, total inductance is R plus XL minus XCJ. Put the numbers in rectangular form as 5 minus 5J. Converting that to polar, you should have got 7.07 ohms, angle minus 45 degrees. This format is important. Units in there, followed by the angle symbol, followed by the angle. In complex rectangular number form, the units go on the end. Please don't leave the J off. I've seen several problems work where suddenly J disappears and then it comes back again later on. Make sure you're consistent with your notation, please. So then we can calculate the current. The voltage is 60 angle 0. We'll assume angle 0 if no angle is given. Okay, divide that by the complex current. And this here is 0 minus 45 degrees. The two negatives make a positive angle. Yeah. We know the capacitive reactance is bigger than the inductive reactance, so the overall circuit is capacitive, CIVIL, current is lead and voltage. We got the signs of our numbers correct. Yep. Then we can calculate VR by multiplying that complex current by the 5 ohms. We multiply the 8.49 by 5, and then we add the angles. There's no angle associated with the resistance. So you should get 42.5 angle 45 degrees. VL is I times XL. XL is 10 ohms, and we remember for an inductor it's a positive 90 degree angle. So you end up with 84.9 volts at 135 degrees. And then lastly, VC is I times XC, so 8.49 angle 45 times the 15 ohms angle minus 90 for a capacitor. That brings in 127 volts angle minus 45 degrees. You look at those values and you say, hang on a minute, 42 volts, 84 volts, and 127 volts do not add up to 60. But that's because they're all acting at different times. They're all at a phase of each other. We need to confirm Kirchhoff's voltage law, which says VR plus VC plus VL must equal the voltage you're putting on the circuit in the first place. We need to convert each one of those to polar form. So we've done a polar conversion, a rectangular conversion on each of those, like so, and then add them all up, and you just simply add the columns up. So we got 90 minus 60 plus 30 is approximately 60. It's only ever going to be approximate because of random errors and conversion errors. And then we got plus 30J, plus 60J, and minus 89, minus 90 is roughly equal to 0J. That's the 60 volts at 0 degrees we started off with in the first place. Okay? All comfortable with that? What? Everyone got everything down they want from the board? Yep. Right. What we'll have a look at now is RL C parallel. So, current wise in here, we've got a current there, we've got an IL, and an IC split. Just I haven't put it on there yet. We'll have the same 60 volts as we had in the last problem. So, for that circuit, to calculate the total impedance for a parallel circuit, calculate the total current, I flowing here, calculate the separate currents IL and IC, and from the results of part C, convert and confirm that Kirchhoff's current law is being obeyed in the parallel circuit. Yep. So get your start and then I'll let you carry on. So how can we calculate ZT in this particular circuit?
Will it be obviously 5 at your resistor and
Let's have it in terms of let's have it in terms of ZR, ZL and ZC for the time being.
ZR and ZL plus together? Or add together? What I'm trying to remember the next bit.
I recommend you use product over sum here. Yep. So that's the total resistance of that. Those two added together, isn't it?
Yeah.
We multiply that by ZC, and then underneath we're going to be ZR plus ZL. Again, it's the impedance of those two in series plus ZC. So we basically add them all together on the bottom line. That's products multiplied together. So we multiply this leg by that leg over sum, which is all of them added together. Anybody not understand that?
So does the phasor diagram work the same way as the
If you wanted to draw a phasor diagram, what do you think you need to do, Callum?
Well, if we follow the rules.
If we're drawing the impedance phasors, yeah,
Yeah.
what you need is,
Quite needed.
you're going to have R, yeah, in series with XL. And you're going to complete a parallelogram, yeah. And then you're going to combine that with the ZC. It's not so easy with a parallel circuit. Yeah,
So you still want us to draw one?
I wouldn't worry about drawing one here.
Okay.
Alright? You'd probably better to draw one for the currents, in a way. We might see if we can draw one at the end and so you can just see how it works. Alright?
So you think in that situation, if you're minus in the angle, if the other minus in the angle for the capacitor, the one.
Yes. Yeah. So, ZT, what have we got? What's the impedance of the inductor and resistor? Is 5 plus 10J. We've got to multiply that by the impedance of the capacitor, which is 0 minus 15J. That's the top line of that fraction. Yeah. Bottom line of that fraction is 5 plus 10J. That's those two combined again. We're going to add on 0 minus 15J. Now, we want to multiply this top line. We'll leave that for a minute because we want to be better off with that in a different form. We want to add these two together. So let's do that now. So a ZT is equal to, leave the top line as it is. Five and nothing is nothing. It's 5, sorry, plus 10 minus 15 is minus 5J on the bottom there. Right, now, guys, what we've got to do is multiply this numerator terms, and then after we've done that, divide that denominator into it.
Would you
So what would we be best to do?
convert them to into rectangle?
Convert all to polar, yeah.
Right, even bottom?
Yeah, because you've got to divide that into the top line eventually, so you get a polar result. Convert all to polar. If we do that, we get a top line that is 11.2. Please check these, just in case I get it wrong. Angle 63.4 degrees. I'm going to multiply that by 15 angle minus 90 degrees. And then eventually we're going to divide that by 7.07 angle minus 45 degrees. Negative 5J must be minus 45. Yep. So multiplying that top line out, 11.2 times 15 is 167.7. Angle 63.4 minus 90 is minus 26.6 degrees. I'm going to divide that by 7.07, angle minus 45. I think you can carry that on now from there. And find the total impedance in polar form. Whether later on you'll need it in rectangular form is unsure at this stage. Alright. Total impedance. We've got a parallel circuit, so we're going to use product over sum. We've already been through that bit. And eventually we multiply the top line out to 167 angle 167.7 angle minus 26, and then divide in the denominator and end up with a total impedance 23.7 ohms, angle 18.4 degrees. Like I say, watch the signs of these numbers. So minus 26.6 minus 45. So the two negatives make a plus. If you're unsure, put it in full form in your calculator and you'll get the right answer. Alright? We then take that total impedance and divide it into the voltage applied using Ohm's law in polar form to calculate a current of 2.52 amps, angle minus 18.4 degrees. Yeah? And is that circuit overall inductive or overall capacitive in nature? CIVIL. The voltage is at 0 degrees. The current's at minus, so it's lagging it. Current lagging voltage, capacitive. No.
Oh no.
No, after is lagging. Inductive. Overall inductive. What here?
0 minus.
No, minus 18.4.
That was
B.
that was the
That's B, that is. The current is minus 18.4 angle. The overall current.
Oh, sorry, yeah, I was looking at the wrong.
Yeah?
Yeah, I've read that. I was
Alright.
looking at the wrong.
So, Callum. Then C, calculate the current through the inductor as the applied voltage, which is the same as the supply voltage, divided by the impedance of the resistor inductor in series. So I've converted that denominator into polar form and then done that division and ended up with an inductor current of 5.3636 amps at angle minus 63.4 degrees. Then calculate the capacitive current. Again, the supply voltage divided by XC. XC is 15 ohms, angle minus 90 degrees for a capacitor. Divide that into the voltage, we get 4 amps, angle 90. For D, convert IL and IC to rectangular, so I've done that there. 2.4 minus 4.7J and 0 plus 4J. Hang on, I've got a sign wrong there. That should be minus 4J. Should it not? Oh no, wait, that's the current. That is plus 4. Capacitive current, yeah, positive angle. add those together, we come up with 2.4 minus 0.79 J amps. To see whether that's the same as the current we calculated earlier, convert that back to polar, we get 2.53 amps, angle minus 18.2. Is that more or less the same as the total current we calculated in the first place? Yes. Allowing for the errors of going backwards and forwards with the polar and rectangular conversion, it certainly is. Alright? One more little thing I want to cover this week, and then next week we'll just have a look at using Thevenin's theorem to analyse an AC circuit, and then we'll move into revision. Alright? So, series resonance. Right, we know that XL is equal to 2 pi FL, and that's also equal to omega L, because we know that omega is equal to 2 pi F. Yep. And XC is equal to 1 over 2 pi FC, or we can write it as 1 over omega C. Now resonance is about what's called the resonant frequency. At the resonant frequency, FR we'll call it. Okay. XL, the inductive reactance, is equal to XC, the capacitive reactance. This is where, in that phasor diagram that we drew before, there's our resistance, R. We've got an XL upwards that is the same size as XC downwards. Therefore, the overall reactance X is 0. And all you're left with is the resistance at resonance. Because these two quantities, XL and XC, cancel each other out. And we can use this fact that XL is equal to XC at resonance to determine what the resonant frequency is. Because we can write XL as omega L, and we can write capacitive reactance as omega C. Yep. What we need to do now, let's call that, that shouldn't be omega L, it should be omega. The omega value at resonance and that should be, sorry, L, omega RL, omega RC. That's better. I've got it right now. So what we need to do is get those two omegas in the same place so we can find omega R. So what do I need to do? Back to first year rearrangement of formulae now. I want to get, either get that omega R with that one, or that one with that one. If I multiply both sides by omega R, what happens over this side? That and that cancels. So we're left with, what is omega R times omega R? So we can write omega R squared times L is equal to 1 over C. What's the next step towards getting omega R on its own?
Move the L across. So
Yeah, divide by L. So we get omega R squared is equal to 1 over LC. And the last bit, square root both sides. So that gives us omega R is equal to, and if we square root the whole thing, let's just put that over here, 1 over LC square rooted is the same as the square root of 1 over the square root of LC. So what you would normally do is write that like this, 1 over root LC. So that is the resonant frequency in omega form. What we could now do is instead write omega R as 2 pi FR is equal to 1 over root LC. And now if we can move the 2 pi, we've got a formula for the frequency, the resonant frequency in hertz. Yeah. So we divide by 2 pi. So we end up with the resonant frequency is 1 over 2 pi root LC. So if we know the capacitor and the inductor values in a circuit, we can find the resonant frequency of a circuit. We're going to move on to a bit more about that in the second half of the year for paper 2, because we're going to be looking at complex waveforms. That's where you got 2 or more sine waves added together, and we're going to look at the implications of one of the harmonic frequencies coming into resonance with moving into series resonance position and what that could mean for the circuit. Alright? But at least you know what we mean by the term resonance now. Always at resonance, XL and XC are equal magnitude. You need to be careful about that. They haven't got the same complex value because one's a plus 90 degrees and one's a minus 90 degrees. But when they're equal size, magnitude, they cancel each other out.
Yeah.
Alright?